thank you all so much for having me. This is fabulous. I always feel honored when anybody involved in category theory wants to have me speak. So I kind of consider myself as a category theory maybe user as opposed to a theorist, but it's beautiful and wonderful, and it's created a lot of interesting directions in my research that I'm hoping to tell you about. So most of the work that I'm going to tell you about today is work with my former PhD student, Anastasio Stefanou. So he was really instrumental in building a lot of the theory I'm going to talk about. But just to give you some context about me, so I work in data analysis. So I do topological data analysis, and the general game plan is trying to find shape and structure in data. And so you start to sort of like bump into things related to category theory, but it's not quite as obvious about applications and how they're going to show up. But sort of where I've been using it most recently is understanding how to compare some of the signatures of the shape of data that we use in TDA. And so the viewpoint that I tend to take for most of these TDA projects is you're trying to take some sort of input data, represent something about the shape and structure in some sort of summary structure. And then the goal at the end of the day is to do some sort of analysis on it, right? And so if you're going to do analysis, you really need to understand things about noise and distances and probability distributions and things like that. And so a lot of the work that I've been doing has been essentially in building metrics for these sorts of structures. So in particular, a lot of the graph-based structures, so in this case, things like mapper graphs, Reeb graphs, merge trees, contour trees, if you've heard these terms, it turns out that you can take this really nice categorical viewpoint and then essentially steal some ideas via category theory from some other ways of building metrics to build metrics on these other categories. So let me give you a bit more specifics on the sort of objects that I like to think about. So a lot of times I view my input data as being some sort of what we tend to call an R space, or you can think of it as objects in a slice category, data that's given as some sort of topological space with a real valued function. And so for the purposes of my pictures, I tend to draw my pictures so that the function is implied by height. So here I've got a massively overly nice topological space. Function is given by horizontal, or I guess vertical coordinate, and I can look at things like trying to figure out how connected components change over these things. Let's find out if I've got my annotation. Oh, I do. Fabulous. All right. So the way that the Reeb graph, which is this one construction that's showed up since the whatever it is 40s, I think, from constructions in Morse theory, is to look at level sets of a function. So if this is a function value a, I can look at the level set of this particular function. I can create a equivalence relation on the level sets of this function based on whether or not 2 points are in the same path connected component. So in this case, those 2 points over there in the same path connected component. I can take the quotient topology, and so if this was a space X and that's a space Y, or point X, point Y, I've got the point, which is the equivalence class of all of the values in the same connected component, and poof, I get this output object. Now, of course, we're all mathematicians, so we know that nothing is ever this nice. So even though I'm calling this thing a graph, the first thing to notice is that I have to make a lot of assumptions before the output construction here is in fact a graph-like structure. The second thing that I'm going to use a lot is the fact that this topological construction inherits a function from the original space, right? So if I've got the point X in my connected component over here, let me get my pen back. All right, if I've got my equivalence class of points X over here, of course, every point has the same function value. And so of course I can define, I guess in this notation, F bar of the equivalence class of X is just, well, whatever F of X was, and that's well defined and everybody's happy. Right, so the end result of all of this are these objects that are basically graphs, what I would think of as topological graphs, maybe one-dimensional stratified spaces if you prefer that, where I've got these functions defined on them. And so when I'm using these in some sort of data analysis application, what I want to do is to try to build metrics, right? So the idea here is that I should be able to take two of these input Reeb graphs. So I'm given two Reeb graphs. So I'm going to write my notation as G comma F. So this implies the graph and the function defined on the graph. I give you two of these things. The distance should be 0 if not only you have the same underlying graph, but you also have the same function defined on that graph. And then from there, you should also be able to sort of understand perturbations and nearby things accordingly, right? So if I have, you know, two graphs that are pretty similar, so in this case, the combinatorial underlying graph is the same, but the function is different. These should be non-zero distance from each other, but should at least be relatively close, right? And so this one also should be relatively close to the other ones because, you know, not too much perturbations on the original graph gives me back the third graph. So there's been a lot of work in the community trying to build these sorts of things recently. And so a lot of different techniques coming from a lot of different backgrounds, right? So in particular, there's been 4 major options that I think have been studied the most in recent years. So these basically take inspiration from other sorts of you know, mathematical tools. So functional distortion distance takes inspiration from looking at things like the Gromov-Hausdorff distance. There's an edit distance variant that's basically the same if you know what graph edit distance is, some variant of that. The bottleneck distance, which is related to looking at related persistence diagrams. And then what we're going to look at, which is the interleaving distance. And so these, there's been a bunch of papers and work recently trying to understand how all of these things are related to each other. But for the purposes of today's talk, I'm just going to focus on the interleaving distance. All right, so here's the explanation I give of this whole setup, especially for non-category theorists. But the basic idea is as follows. So the way that I would think about the objects in my category is sort of getting close to how I would think about defining flows on metric spaces. So if you give me some metric space with a distance, what I'm going to call a continuous flow would be some sort of continuous map where I can take an input value epsilon, and I can essentially take any object in my space and flow it forward by epsilon. And that should have some nice properties. For instance, if I flow by, I lost my pen again. If I flow by nothing, right, I should get my same thing back. And if I flow by A and then flow by B, that should be the same thing as going forward by A plus B, right? And so what we're going to do is we're basically going to take all of the definitions in here and swap them out with objects in a category, right? So if you give me some category, I'm going to define basically a special case in my flow, so a strict flow, to be this functor where I have, again, I have an epsilon parameter that I can work with. So I've got this epsilon back here. I have a way of flowing objects in my category forward, so I can take my original object x, and I have a definition of what f sub a of x is. And this should play nice in the same sense, working together with all of these functors as, you know, what we were doing in the metric space case, right? So if I flow by nothing, that should be the same thing as leaving my object alone. And if I flow forward by A and then by B, that should be the same as the functor that I get that goes forward by A plus B. Right. Now, it turns out that this is a little overly restricted to do a lot of the things that we were trying to mess around with. Oh, sorry, let me mention one other thing. Again, this is in front of a bunch of people who understand categories. The first thing that people that don't do category theory tend to miss in this whole thing is that I have some additional structure that I'm going to make use of. In particular, I have a category, so I have morphisms. And so I have, not only do I have a way of flowing forward objects, I have morphisms that go from one object to the next. And so I can sort of keep all of these relationships, all the structure of all these relationships together to be able to form what we're going to talk about in a bit. Right, so you can generalize the heck out of this, of course. So if I swap out everything I had on the previous slide in blue as equalities with some sort of natural transformation instead, right? So I still have some sort of functor that's got an input value epsilon, and I get these sort of maps on your original category. All I've done to change here is that now instead of having flow by nothing be equal to my original space, I just have to have a natural transformation from the identity. Similarly, if I go forward by whichever one that is, that's zeta, whatever, A plus B, right? That should be at least related to what I have if I go forward by A plus B. Right. Again, for the purposes of this talk, I am mostly not going to use this particular variant because it sort of shows up in some more, actually not even that many pathological cases, but basically what you have to do then is if you have natural transformations instead of equality, you have to go check a bazillion things to make sure everything plays nice. And the diagrams on the right are basically what happens if you go make sure that everything plays nice with everything else. So it turns out that these sorts of constructions show up a lot in practice. And in particular in some very nice simple settings that we're going to talk about for at least the first bit of this talk. So first off, if you give me the space of Euclidean space, so I've got Rn with my inequalities as poset structure. So if I can define a flow that's essentially just shift by epsilon. So in this case, I mean add epsilon to every coordinate. If you're in R, that's just shift forward by epsilon. Turns out that this satisfies all of the definitions of flow that I had before. I can do things like, so this notation on the left is actually subsets of a metric space. So M is a metric space, D is a metric on the metric space, and then I'm looking at subsets with inclusion as my poset structure. And again, if I take subsets of my metric space and I look at changing that subset by thickening by epsilon, so essentially just spread out to all the points that are epsilon away, that also gives you a flow operation. The other one that tends to show up a lot in the kinds of things that I think about are functors from R to vect or from RD to vect. Again, if you do anything with topological data analysis, we like to study things like persistence modules, and these are basically representations of persistence modules. And in this case, precomposition by this shift functor, the S epsilon, is exactly sort of what we tend to have show up in some other constructions. So once you have one of these, this sort of overarching starting structure, right? So once you have this category, I can define a metric on these categories as follows. So I'm going to say that two objects in my category, so right now my objects are my capital X and Y. I'm going to say that they are epsilon interleaved, or at least weakly epsilon interleaved, if I can build a diagram that looks like this thing. Okay, so let's try to figure out what's going on in here. My original flow data, let's see where to go. My original flow data right now is the stuff in red. So I've got all of my sort of coherence, transformations, information that came with my original flow. I've got my induced maps from my original functors. So this data all kind of comes from my initial flow construction. The game with epsilon interleavings is to go see if you can find a pair of maps. In this case, I've got them denoted phi and psi, for which, okay, you get some induced maps from the functorial structure. Can you find a pair of maps that makes this whole diagram commute? And the thing to notice here is that I've got this epsilon parameter built in, right? So I am basically allowing myself to flow forward one of the objects by epsilon, and then trying to see if that gives me essentially enough wiggle room to build this diagram. And so the idea here is that if you then look for the best possible epsilon, or the femum overall epsilon, for which I can build one of these diagrams, this is what we call the interleaving distance, right? So give me a pair of objects, X and Y in your category, look for the smallest epsilon for which you can come up with an interleaving between them. Now, again, I'm calling it a distance. Of course, you have to be careful about that. So it turns out that just with the initial flow assumptions, this construction will always give you an extended pseudometric. All right, so extended here means that it could be infinite because it's possible that I can't build that diagram. And pseudo means that it's possible that two things could be distance 0, even though they're not actually the same. All right. Now, for the purposes of what I'm going to do, I think the examples I'm working with will end up being extended metrics, not necessarily extended pseudometrics. I love this diagram from this paper. So when you go around trying to prove that this thing gives you this extended pseudometric, you basically have to just go check all of the metric properties. And this is how you prove, for instance, the triangle inequality. So the point of this slide is basically that you've got a lot of weird, I think that the beauty of this work is in the definition, right? Where you've got the right definition, and after that, checking things turns into essentially, building some commutative diagrams and checking that stuff works out. It's mostly following your nose, but it's non-trivial. Okay, so let's go back to examples because that's my happy place. So before we talked about all these examples of categories and flows, so it turns out that if you take the categories and flows I talked about before, we actually spit out some very standard metrics. So for instance, if you give me Euclidean space with this shift operation for the flow, the resulting interleaving distance is actually just L infinity distance on Rn, right? So component-wise differences and look for the maximum possible. The subset of, the set of subsets of a metric space, again, with this thickening operation where you take a space A and you spread it out by epsilon, the result when you construct the interleaving distance via this other stuff is actually just the Hausdorff distance. So again, you can start seeing some relations between these because again, it's some like, you're looking, the distance ends up being some like worst case epsilon over like looking for matchings. Again, because, you know, if you're doing stuff in TDA, the construction ends up spitting out interleaving distance for persistence modules. So everything I'm going to talk about today is actually inspired by the sort of definitions and constructions started by trying to generalize a metric on persistence diagrams and persistence modules via category theory. That was some beautiful work of Peter Bubenik, who I don't know if he's here right now, but I know he's speaking later in this session too. But a lot of these ideas are essentially a categorical translation from some of these other setups. Okay, so you can build this thing in a bunch of different settings. So for this talk, at least, I want to show you how we can use this construction I've built to create metrics for graph-based signatures. So the Reeb graphs I was talking about in the beginning, especially. Okay, so in order to do that, I got to tell you what my category is, right? So my category is going to be Reeb graphs, where by a Reeb graph, I mean the pair of data that comes with having both the space and the R-valued function defined on the space. My morphisms are going to be given by function preserving maps. So the rule with these pictures is if I have a point X at one Reeb graph, move my videos out of the way. If I've got a point at X and one Reeb graph and I want to come up with a function preserving map between the two of them, this is going to get sent to a space, and the other one, that's, well, you get two choices in this particular option. I could either get sent to that point or that point because they're at the same function value and nothing else. So things to notice, for example, if you don't have any point to get sent to, right, there's no possible maps whatsoever. So actually, let me make my example a little different, right? So if my example actually had a stretchy bit up here, there would be no possible function preserving maps from one to the other because this point Y up here has nowhere to go. Okay, so this is going to be my, my category that I'm working with. So the goal here again is to try to use this setup with the interleaving distance setup we had before in order to come up with a metric. And so the easiest way I think to view this, okay, the easiest way for people with a category theoretic background to view this is to swap out these geometric objects for some set valued co-sheaves and show that this basically encodes the same information and then run from there. All right, so what are we doing with this? All right, so here's my sort of pictogram of how this equivalence works. So if you have an input graph, so my pictures are now sideways, so now function value is apparently horizontal. If I've got some input Reeb graph, what I can do is I can look at the inverse image over intervals, right? So what's going on in here is I have, so this is F inverse of I, if this was F, right? So I can look at the inverse image over any of my possible intervals. And that's, you know, already interesting, but more than I want at the moment. So what I'm going to do is I'm going to replace each of those with the set of path connected components. So if this thing was F inverse of I, I'm going to look instead at pi naught of F inverse of I. Okay. And so if I take any interval and send it to this thing, this gives me this set valued co-sheaf that I can work with. Now, I said before that you need things to be, I need to make some assumptions on my input data in order to end up with nice graph output structures. Though the definition we ended up working with were S-constructible co-sheaves. So here's the idea. If you give me a set of points in R, so S is my set of points in R, they're the green circles on the bottom here. I'm going to say that a co-sheaf is S-constructible if I look at any interval, oops, come here. If I look at any interval, So let's call this thing I, and maybe this thing is J, right? As long as I and J intersect the same set of critical values, the same set of points in S, then I should have an isomorphism between the connected components. So in this particular picture, my number of connected components should not change whether I'm looking at that view or at that view, right? So this is essentially a way of working with nice enough co-sheaves to do what I want. Oh, look at that, that was nice of me. Okay, so so this is my other category we're gonna work with. So the objects of my constructible co-sheaf category are going to be these constructible co-sheaves F that go from int to set and natural transformations between them. So the first thing that you have to go double check is that you get an equivalence of categories, which is, you know, basically again, following your nose. So if I turn my Reeb graph into a one of these constructible co-sheaves, it turns out that you do get this equivalence of categories. This is one of these folklore theorems that was around and sort of in pieces all over the place that we sat down and wrote down, but this is a nice equivalence to work with between these two objects. The second thing that you need to do is you need to build some sort of flow on here. So in this case, we can take those ideas of thickening, right? So if you give me an interval J, I can thicken it by epsilon to get the interval A minus epsilon B plus epsilon. If I pre-compose with that operation, that gives me a flow on these constructible co-sheaves, right? So given an input co-sheaf F, I take any interval that I want to work with, I thicken by epsilon, and then I see what connected components I have, right? And it turns out that you can build this into that whole structure I had at the very beginning, and then building metrics comes down to essentially trying to search around looking for diagrams like this, right? Again, I'm in a nice enough category where this is a strict flow as opposed to a more general flow, right? So I get a simplified ladder diagram. But the game is always go find phi and psi for which you can build a diagram. It looks like this, right? And again, this is now, you know, the second time that you've seen a picture like this, but all I've done is swapped out which particular category I'm interested in, right? If you give me two of these constructible co-sheaves, we go looking for the best possible epsilon for which I can build one of these ladder diagrams, right? And again, for me, because I am happier when I can do things with combinatorial looking graph-like objects, it turns out that you can actually do this whole thickening procedure on your original graphs and get the same output. So if I instead wanted to work in the category of Reeb graphs, where I have all those function preserving maps, I can define a flow on Reeb graphs via the following procedure, which is you can take your graph, cross it with an interval. Now my pictures are drawn still so that function value is height in this case. And so each point, right, x gets sent to a point. So this would be x comma 0. This one is x comma minus epsilon. This is x comma plus epsilon, right? I can define a function on this now two-dimensional stratified space by essentially just summing up the values in f of x and however much shift I have in the epsilon bit, and then take the Reeb graph of that. And so the result is I started with a Reeb graph. I have an epsilon parameter, and I get a epsilon smoothed Reeb graph. So this thing also turns out to be a definition of a flow. And again, if you want to keep track of all this stuff, you can keep track of the inclusions. I get induced maps on the original spaces, again, the sort of functorial properties that I want to keep track of. I'm not going to worry about this because I'm getting low on time. But again, you can just plug and play. This is the third time we've seen this basic slide, but the idea is that now if I've got Reeb graphs instead with these function preserving maps, I can look for function preserving maps on from a graph to the smoothed version of the other one I want to compare. And then again, go look for an epsilon that's as low as possible to see if you can come up with an interleaving. You can prove a bunch of stuff about this that is nice for what we're doing. So for instance, this is an extended metric in the case of Reeb graphs. In particular, it does take infinite value potentially. So again, infinite value means you can't build an interleaving. And that happens if and only if you have different numbers of connected components. The other bit that TDA people tend to be really worried about is checking for stability. So in particular, if I give you input data, so in this case, my input data comes as two different functions on the same underlying space. If I were to have one basically be a perturbation of the other, or one is the noisy sampled version of the other, something like that, the interleaving distance between the resulting output Reeb graphs is no worse than how far apart those original functions were, right? So in particular, if f and g are close together, the Reeb graphs representing them are still close together under this metric. Let's see. Okay, yeah, this is, there's a lot of different things we've done with this, again, because the beauty of this whole setup is that once you've got the sort of starting construction, you can start swapping out the objects of your categories and just get metrics to study all sorts of different objects. The kinds of things that I tend to think about are, again, these graph-based signatures, but there's no reason why it would be limited to that. But in particular, some of our recent work, we've been looking at a variation of that smoothing operation that sort of changes how you shift the Reeb graph around by adding a second parameter. And the addition of the second parameter gives you sort of more wiggle room and different choices, a whole family of metrics that you can work with. I've done some work where we did this on merge trees, which are a specific type of graph-based representation. Again, it's still a graph with a function. So again, it should be sort of obvious it's related to the other stuff I've been talking about. But in particular, you can do some really nice things, especially if you're working with labeled merge trees, because you can represent these things as matrices. And again, there's a lot of nice structure going on in there for things to play around with. I've done some work where we are representing these things or using this metric to understand stuff about mapper graphs. So again, this is a construction that showed up a lot in the applied setting where you're trying to build some sort of graph-based representation of underlying point clouds and things like that. Shows up a lot in practice. And some of our other more recent work was basically taking that mapper graph viewpoint and extending this to sort of the general viewpoint where you're looking at some underlying poset structure, which is essentially what the mapper graph is doing with the interval cover, and then using that information to build and understand interleaving distances in this setting. So with that, I think that's it. So again, I want to plug Anastasio Stefanou because he is definitely the mastermind behind a lot of the categorical constructions here. And the majority of the work that I talked about is in these two papers. So the big theory paper is in Theory and Theory and Applications of Categories. And then the specific case of Reeb graphs is here. So with that, thank you so much for your attention.
Thanks very much for your talk. Let's thank the speaker, please. And I'm afraid we have a little time for a comment only.
Okay, I'll just quickly ask or make a comment and you can answer it later. I was just wondering, from what I see here, is there any reason for doing it only for functions to R, or could you also do it with R squared or Rn?
Yes. Oh yeah. Yeah. Okay. So the fast answer is if you want to do the functions to Rn, the Cauchy viewpoint passes through relatively, I'm going to say this without checking all the details, but relatively easily, right? Because a lot of that stuff is pretty easy to do, and you probably want to restrict yourself. There's sort of an implicit convexity assumption in my using only intervals. You would probably want to stick with convex subsets of Rn. The weirdness shows up, and the reason why I haven't gone down this direction is that when you try to pass to the more topological space representations, you then start bumping into sort of the question of like, what exactly does it mean to be constructible? In particular, there's an I'm implicitly using the fact that if I have two different Reeb graphs with two different critical sets, I can use that to get a substratification of the real numbers very easily. But if I have higher dimensional analogs, which are usually called Reeb spaces, understanding how the two critical sets, which are now like these one-dimensional things in the plane, you know, you'd have to be a lot more careful about how they intersect and how to work with it. I'm going to keep plugging this because I really want somebody to do this, but yeah, it's there's some technicalities to work out.
Maybe we can talk a little bit more at the end of the session if you have time.
Yeah, absolutely.
Okay, thank you.
Yeah, you're welcome.
Great, thanks.